So good morning to everyone. I'm Andrea Spolaor from the Institute of Polar Science in Italy. I work specifically in the headquarters in Venice. And today I will bring this case of study that with the name that is climate change and impacts on the climate in Svalbard Glacier. So these works that I'm going to present, it's linked with a lot of topics because there is glaciological measurement, a bit of chemistry, monitoring, modeling, and so on. So it's a case where there is different discipline put together. But however, sorry, my mistake. So before moving into the works that I'm going to present, we need to contextualize where we are working. So in this slide, we can see the Arctic region. And in particular, I mean, this study was performed in the Svalbard archipelago. Svalbard archipelago that is located in the high North Atlantic is particularly interesting because it's at the edge of the sea ice, is influenced by different atmospheric conditions and maritime conditions as well. And in particular, if we look on the central figure where the Svalbard is indicated, we are working in the northwest portion where Ny-Ålesund, I don't know if you ever heard about this research village, is located. So in particular, if we zoom in the area where we are working, this is the, we can say, a portion of the Spitsbergen area. Ny-Ålesund is located in this, where my arrow pointing, and we are working in this ice cap that is called Holte Dalfona. That is one of the higher ice cap in the region. So essentially, there is quite a lot of attention regarding the Svalbard archipelago. And I think most of you have already heard about the Arctic amplification. So the Arctic amplification is a phenomenon where the Arctic is warming on a faster rate compared to the global average. If you look on the chart on the left, we can see in black is the temperature, the average global temperature trend, we can say from the beginning of the 19th century to the current time, while in red we see the temperature in Svalbard. And we see that in the last, we can say, 2 or 3 decades, the temperature in the area of the Arctic is increasing in a much faster rate compared to the global average. However, this red curve that we are looking, it's something connected to the whole Arctic. But if you are looking more a bit in detail on the Svalbard archipelago, and we're still looking on the chart on the left, we see the red curve that show the temperature anomaly compared a reference period that is the 1950 to 1980s. For the whole Arctic. But if you look the blue line where we focalize only on the Svalbard archipelago, we see that while the Arctic is warming between 2 or 3 degrees in the last 2 or 3 decades, the Svalbard has increased the temperature much more, and sometimes, especially for 2020, something like that, up to 6 degrees more than the global average. So the Svalbard is somehow called an hotspot for the climate change because it's changing much faster compared to the Arctic and also to the global average. So it's, as I say, it is one of the warming regions in the world. And also this rapid temperature increase affect the glacier, I mean, all the glaciers that are present in the archipelago. And we also need to consider, why is it not moving? Okay, that one of the particularity of the Svalbard Glacier, they are located at low elevation. So we are below, in the average, we are below the 1,000 meter in elevation high. So this is very exposed to the change in the low atmosphere temperature changes. So they are very exposed to the climate change with all the consequences. So mass loss, increase of water percolation, and so on. So essentially, just to give an idea, I'm working in this context since 2012, and this is a picture of the Kongemann Glacier that is at the end of the Kongsfjorden, taken in August 2012. And you can see that, to give just a reference, this is 3 kilometers wide. And another picture taken always during the end of the summer in 2022, this is the difference that we see between in only 10 years. So the archipelago and the glacier of the archipelago is changing quite fast and quite a lot. And it's really possible to see by your eyes the changes that are occurring at the cryosphere in this area. So before entering a bit into the detail, I need to give a brief introduction of what means a natural archive and an ice core archive especially. So essentially, during the winter, we have the snow accumulation. It accumulates layer by layer, and this snow is able to trap the atmospheric composition. So if the snow survived to the summer melting, so part of the snow or the full snow pack survived to summer melting, during the next year, we have another snow pack that form another layer. And at the end, we start to have like a layering of snow, one over the other, where inside there is good information of the atmospheric composition in where this snow layer has been formed. At the end, this snow that has become compact and compact more and more, it become ice, and we drill the ice, and we collect this ice core archive where in the ice is stored the information of the past atmospheric condition. So we use this archive to study the climate impact on the signal that is preserved within this ice. And just to give an example, on the left panel is a show of a potential signal that we are able to find in an ice core archive. So if we look on the left panel, this one, we really see this oscillation of the parameter where the more negative value of this parameter that is called the water stable isotope ratio, that is a proxy of temperature. So we see that more negative is the winter period, more positive are summer periods. So, and we see this oscillation. So this parameter here, so the water stable isotope, is able to reflect the change in the atmospheric temperature. For example, this is just a kind of, the left panel is a kind of a snapshot, but if you look on the right panel, we see that we have in red, we have the real measurement temperature, so from instrumental point of view, while in red, in gray and black, we have the reconstruct temperature by this parameter. And the two things fit pretty well. So we can extend with the ice core the temperature reconstruction in the past, also behind the instrumental record. However, the reconstruction of this past atmospheric condition or temperature need to have some requirement. We need to find the right spot. It need to be quite preserve the signal, so there shouldn't be too much melting during the summer, so the snow need to be rather preserved. And we decide to go in this ice field that is called, as I said before, the Alta del Fonna, where in the summer period, it preserved part of the snow that accumulate during the winter. So we went to this ice field. We went from 2012, 2015, 17, and 19. So we went for consecutive year. And what we measured this water stable isotope parameter. So this is in 2012, this is 2015 ice core record. So this is divided by year. So, and what we can see is that in 2012, we can see some kind of oscillation of this parameter connect with the temperature, as well in the 2015 ice core. But when we move to the core that we collect in 2017 and in 2019, this oscillation that we were able to see in 2012 and in the core collected in 2015 are completely disappear. So this means that something has happened. The site is not more usable for reconstruct to be used to reconstruct the past climate condition, but this somehow it starts to degrading. So from a signal that we can use in 10 years or less than 10 years is moved from a condition where we can use this site to reconstruct the ice, the past atmospheric condition, to a potential condition where we cannot use anymore. So to study this, how much the climate change is or is contributing to this degradation, we combine this our measurement with additional field measurement. In this case, the mass balance, so how much the glacier on our drilling site is gaining mass or losing mass, can help a lot on defining this degradation of the signal. For example, if we look on the panel C, D, and A, we have in the panel C, we have the annual mass balance. So how much the site gain mass through the year. And we see that we have an increasing of the accumulation of this of the mass at the site, where also during the summer we could have positive mass balance. So also during the summer we have a kind of increasing of snow mass. But however, this is not a condition to help us, because when we speak about increasing mass, we have much more snow that could be present in at the site, but at the same time we could have much more melting. So much more melting, so means having much more water that can percolate into the snow and later in the firn and ice, and really wash out the climate signal preserving the snow. To support these ideas, we can use modeling. This is a model simulation of the water percolation into the glaciers. So the black line is the snow surface. We can say simulate from 1992 to 2023. And we see that where the red line is the isothermal in terms of depth, so how much the 0 degree will go into the snow. And we can see that at some point, moving closer and closer to the recent period, the isothermal, so the 0 degree temperature, going deeper, and also with associated an increase of water percolation, that is essentially the blue color, into the deep of the glacier. So these modelings help to support the observation that we had. Finally, we also have an observation by using the R5 o comunque or the atmospheric reanalysis. We want also to check if to this increase on melting there is a change in precipitation regime. And in this case, on the right panel, we can see if there is a change in the seasonality of precipitation. But from the chart, it seems that the precipitation is rather constant through the last 30 years. So support the idea that the increase in temperature are causing an increased melting, increased percolation, and so kind of a washout of the signal within our archive. Finally, however, one thing that we are still a bit optimistic, although we are not able to see anymore the seasonal variability of this parameter that permit us to check to reconstruct the past atmospheric temperature. When we compile all the 4 records together, so we really overlap the different records together, and we compare with the annual temperature, although we are not able to see anymore the seasonal response to this parameter, to the atmospheric, to the temperature seasonal changes, and we compare that show by the black dots with the annual temperature, we still see that the record that we have, although very smooth, still respond to the increasing trend that we observe in the Svalbard archipelago. So although the signal is going to be degraded and is really deteriorating quite fast, somehow the general trend of the atmosphere is still present there. We are still able to use the site for a general reconstruction of the past temperature variability. However, in support to our field observation, we also use the satellite remote sensing for the cryosphere. And this is very important for the work that I'm doing, because it's give an idea about which is the snow line altitude, so or how much ice has been exposed during the summer. So just to give an idea, on the left panel we have a satellite picture from 2017, where the light blue color is the snow cover, while the blue is the bare ice. While in the August 2023 we have a much less, we can say, snow cover, indicated by the light blue, and much more bare ice exposed. So the satellite suggests that in compared 2017 and 2023, there is much less snow preserved after the summer compared to the year 2017. So this gives an important information when we are going to interpret the rest that we have from the ice core climate archive. As well, we have also the close range remote sensing, or essentially the camera. In this case, giving important when the sat is cloud cover, for example, and give an idea about how the snow change after a specific event. And also this is very important because we are able to identify when a specific event like heat waves approach the archipelago. For example, if you look this one to these differences, we have a picture of the 17th of May 2022 and another picture 23rd of May 2022. So the two pictures different of 6 days. And we see that here the snowpack is kind of uniform and pretty well distributed. But if we put quite a lot of attention, especially in this area, here we start to see some feature, and this is like a water channel that is formed after a rain event that occurred between the 17th of May and the 23rd. So this type of measurement help us to approach and go more into the detail in the evaluation of the data that we collect from the field. Finally, we also have this type of measurement that is the automatic nivometer station. This gives a continuous monitoring, automatic, of a lot of parameters of the snowpack. So we know it's at the coastal site, not on the drilling site, but at least he support our observation, giving an idea of how the snowpack evolve and form during each season. So I would like to conclude. So the Svalbard has an increased glacier mass loss. This study is the first to assess how rising temperature in the archipelago affect climate signal preservation in the ice archive in the Svalbard archipelago. We suggest that the higher temperature boosted submelt and meltwater percolation, so washout of the climate signal present in the ice core climb. And we just remember that this degradation of the signal is happening in 7 years. So I think it's very intense, the change in Svalbard. And another point that I want to raise is that to do this type of study is essentially a multidisciplinary approach, because without all different pieces of the puzzle, it's very difficult to arrive at a robust conclusion to define how the impact of the climate change affect the ice core climate scene in this archipelago. With that, thanks for your attention, and I think I was a bit in delay.
Hi, Andrea. Thanks a lot for your presentation. And yeah, no worry about the delay. You told us about it, so it's okay. So yeah, it was really interesting. We have a few questions for you, so we will go to that part now. So the first one being a more general question about your study in general. Have you looked into the role of marine heat waves in the Barents and Nordic seas?
Okay. Do you need to reply or you need to read all before?
Sorry?
Do you need to reply to each by one?
Yeah, one by one.
Okay.
Yeah.
So to reply to this question, I mean, we thought about the marine heat waves. The things that this paper, this work, was more connected with an atmospheric component more than a marine component. So, and we thought that is interesting to look at the marine heat waves. However, it makes all the story very heavy to digest also for a potential referee, and there is too much things to put together. For sure, the marine heat waves has a role in controlling the climate and the events in the Svalbard archipelago, but we were more focusing instead to the marine heat wave that are a bit slower, we can say, to the atmospheric heat wave. So this kind of rain or snow event or this like specific condition that occur quite often. It occurs between 1 to 5 times every year in the Svalbard archipelago that bring this mild air from the southern latitudes. So we are more focusing on the atmospheric counterpart than the marine part. But I think it's something to be explored, and it's a good question.
Okay, thanks a lot. Yeah, it makes sense concerning the size of the work also. Another question, I think it was for the beginning of your presentation. Do you use a software to measure ice ice sheet lake cover or glacier density? Is it available online for users to use and download?
Okay, the question that do you use software to measure ice sheet lake cover?
I
This
think
no.
yeah.
Is no, because I'm not a modeler, so I'm not using this type of software. I want to be honest. The glacier density, it can be I can say modeled, but we use the measurement because the density is not an exponential line as we can say a theoretical exponential line. This type of glacier has a lot of firn ice layers, so there is a lot of discontinuity in the density increase, and it's not easy to reproduce. So we prefer to measure the density because it's in 20 centimeter, you can have a layer of 0.5 or 500 kilometer per meter cube density and like 0.900 kilogram. So it's very variable. Obviously, it increases with the depth, but it's not so linear as a classical density increase.
Okay, thanks a lot. Okay, another question, more specific one. Have you considered using microwave LST data to look at the emissivity differences over the region, AMSR and SSMI? Emissivity could help with classification.
We thought, because I have some people working with this type of measurement, but as said, it's very complex sometimes to connect the field data, atmospheric reanalysis, ice modeling, and also with this type of measurement. So it's something that is interesting. Everything that can be put together and give some more information is very helpful. But we need to be also realistic when we produce a product like the paper that they present. So we need to be at some point focusing on some part. We are doing some extension using these techniques, but it takes a bit more time.
Okay, thanks a lot. Okay, and so the last question for now, have you assessed whether this increased ice loss is attributed to increased melting or to increased ice discharge due to calving?
Okay, this is both, I want to say, because for example, I show a picture showing the difference between a glacier in 2012 and 2022. This is a floating glacier, so there is a lot of calving over there. And part of this glacier mass loss is due by calving. But as well, so I would say both, because there is most of the glacier in Svalbard are temperate. So if you have melting, the water percolate almost through the entire glacier and will be discharged into the seawater. So I would say that is both. I'm not sure if which is winning. I mean, if it's more ice loss or the increase of calving, for example. So there is another thing that the increase of melting increase the speed of some glacier. So there is some glaciers start to surging because it's like you have a lubrication effect on the bottom. I think that is not super easy to assess which is if increase is melting or increase ice discharge. So for example, for the small glacier, like the ground glacier, that there are a lot of small glaciers in Svalbard, the melting is winning. So there is no calving in this glacier, and they are losing like at the bottom is losing up to 3 meter water equivalent per year. In the upper part, a meter. So this is fully melting. Obviously, the glacier that are discharging or arriving into the fjord, into the sea, this is different because there is the calving that is quite important, but as well, I mean, also the melting as an effect. It's difficult to say. I mean, there are some studies in specific glacier where it seems the melting is a bit more efficient, but obviously this is just one case over 1,000 glaciers in Svalbard.
Okay, thanks a lot for the explanation. I think it's clearer for the participant now. So that was the last question for you, Andrea. Thanks again